Science. DNA could revolutionize how we store our data. The age of AI will rely on massive volumes of data that can be easily stored and retrieved, and bioscience may have an ingenious solution. A scientist examines a DNA, deoxyribonucleic acid, profile on a screen. Photographed by TechImage, Science Photo Library. Text by Maddie Bender. Illustration and animation by Diana Marquez. Video research by Patricia Healy. August 21, 2025. A scientist examines a DNA, deoxyribonucleic acid, profile on a screen. Photographed by TechImage, Science Photo Library. Text by Maddie Bender. Illustration and animation by Diana Marquez. Video research by Patricia Healy. August 21, 2025. Shakespeare's entire catalogue of sonnets and 8 of his tragedies, all of Wikipedia's English-language pages, and one of the first movies ever made, scientists have been able to fit the contents of all these works in a space smaller than a tiny test tube. They didn't somehow miniaturize them, though. Instead, they used DNA, the building block of all life, to encode the information in these creative works and store it at a microscopic scale. As humans adopt advanced tools like artificial intelligence, tomorrow's currency will be data. Already, tech giants like Microsoft are raising billions of dollars to construct data centers for AI. And there's a very real storage war scramble underway right now to figure out how to preserve and safeguard exponentially increasing amounts of data. Football field size, gigawatt energy-sucking data centers are one option. Or DNA storage could be an energy-efficient, compact solution. Ancient DNA, from Neanderthals to the Black Plague, is transforming archaeology. Step 1. Computer storage. Step 1. Computers store each letter or pixel of digital data in combinations of ones and zeros. We typically think of DNA as a blueprint or instruction booklet. Its sequences of As, Ts, Cs, and Gs tell molecular machines how to build the fabric of our very beings. DNA storage flips this paradigm on its head. Computer data make up the inputs, and DNA is the end product. A handful of startups are working to perfect the conversion of binary computer code into physical DNA strands, and in doing so, take a shot at disrupting the multi-billion-dollar storage industry. Here's how they plan to move the industry away from microfilm, microfiche, disks, and servers. Traditional data storage relies on constant migration to prevent old data from degrading or the technology it's stored in from becoming obsolete. Varun Mehta, CEO of Atlas Data Storage, compares long-term data storage to painting the Golden Gate Bridge. By the time you've gone from. In practice, DNA storage involves several steps: deciding on a code, making the DNA using a process called synthesis, and storing the resulting DNA strands. DNA storage methods also include ways to categorize the stored strands and convert nucleotide sequences back into information that may be compatible with computers or accessible in some other way. Though industry members formed the DNA Data Storage Alliance in 2020 in part to set standards, companies in the DNA storage space still approach each of these steps in slightly different ways. This archaeologist hunts DNA from prehistoric diseases. First, to store information as DNA, scientists have to determine how the data will be translated. DNA is a base 4 system. In contrast, computers store and process information in binary. Instead of assigning a 1 or a 0 to each DNA nucleotide, an A, C, T, or G, you could instead assign a particular combination of 2 digits to each base, so an A might stand in 400, C01, T10, and G11. Theoretically, this means every DNA nucleotide can encode up to 2 unique bits. In practice, the system isn't as efficient as that. There are certain combinations of DNA nucleotides that are less stable or otherwise undesirable, and different chemistry protocols exist for turning bits into DNA bases. Catalog, one DNA storage company, announced in 2022 that it had encoded 8 of William Shakespeare's tragedies into a single test tube. To do this, scientists had to translate about 207,000 words into strings of nucleotides using a class of enzymes called recombinases. They claimed their DNA building machine, Shannon, encoded the plays into millions of nucleotides in a matter of minutes. To each of those words, you associate a random bit vector. A bit vector is just a sequences of ones and zeros of a fixed length, explains Catalog's head of DNA computing, Swapnil Bhatia, in a video for the company. The word rose might have a random bit vector stretching 1,000 numbers long, and different companies will have different ciphers for translating words into ones, zeros, and nucleotides. Step 3, Synthesis. Step 3. These letters are one part of the nucleotides, the building blocks of DNA. Today, scientists are using th. Read more. DNA synthesis, the step of actually creating custom DNA strands, is another place where companies diverge in their methods. Catalog uses the principles of inkjet printing to exude tiny droplets containing pre-made DNA fragments. In dog DNA tests are on the rise. But are they reliable? Step 4, Storing the DNA. Step 4. The strands are archived in material like sealed vials or other materials. Storing and preserving these synthetic strands presents another set of hurdles. Catalog and Atlas store DNA samples inside metal capsules, where the strands are not exposed to the elements and degraded. To convert DNA back into bit form, one can sequence it, using the same technology that powers genetic testing like 23andMe. This method can't be done indefinitely. Eventually, the sample will need to be copied over again to restore it. To create longer-lasting, accessible storage, some groups are working on fluorescent tags. Shining a light on the samples can tell researchers information about a given sample at a glance, the same way metadata can help us organize computer files without having to open them. If companies are able to surmount these challenges, a DNA storage system would take up a fraction of the space of traditional storage methods. The theoretical limit is astounding, Meta says. You could fill 50 petabytes worth of data in an Tylenol-sized capsule, or roughly 50,000 times as much data as an iPhone can store. Step 5, Retrieving the data. Step 5. When it's time to retrieve digital data from DNA, an algorithm converts the archived information back to read more. Storing information in such a small physical package raises philosophical questions about the purpose of storage. Could a storage device itself serve a purpose? Scientists have theorized and created proofs of concept of fabrics and everyday items like glasses that contain DNA-stored information. The company Catalog has a branch dedicated to DNA computing to search and analyze synthetic DNA without first converting the information encoded in it back into bits. There could be some advantages to working with data in DNA form, rather than moving from one end to another, like a computer processor does. Working with the data can occur in many places at once in parallel. DNA's status as the basic building block of life may someday make it one of our most durable technologies, Meta says, because it means it isn't going anywhere. 1,000 years from now, there probably will not be any DVD players. In fact, it's hard to find a VHS tape player anymore. But that's never going to happen with DNA, because we need it for our own health, he says. We'll always have that technology available.